Saravanan, Jasper Sweeter, Chenrui Zhang, Eric Zhang, anybody not get paper? Oh, okay. The average on the exam was about 73. And I'm thinking A is greater or equal to 80. B felt like greater or equal to 65. Something like that. Questions about anything? The last time I was describing this wild function called Thomae's function, and I thought I'd say a few more words about it. It was that t of x is equal to 0 on irrational numbers. So that would be, let's do it on the interval from 0 to 1, minus the rational numbers. And it's equal to 1 over q if x is a rational number, and it's equal to p over q, where p and q are positive integers with no common factors. So that would be p and q, and there's a unique way to do that. So that would be natural numbers, no common factors. And let's see, of course, we make 0 and 1, you have to, are kind of exceptional. T of 0 is 1, and t of 1 is 1. Then this wild and crazy function is continuous at every irrational number. So t is continuous at each x that's irrational. And it's discontinuous at each rational point. In 0, 1. It's easy to see that it's not continuous at a rational point, because at a rational point it'd be something strictly positive, and there'd be irrational numbers close by where the function would be 0. So there's no way it's continuous at a rational point. But the interesting thing is, why is it continuous at the irrational points? Okay, it's 0 at an irrational point. And here's the way I like to think about it. Graph the function. At 0 and 1, it's equal to 1. There's 1. And then you think, okay, at a half, it'd be a half. And then if you think about where is it going to be equal to 1/3, that's a half. Well, let's see, it'd be 1/3 at 1/3, which is right about here, so that's a half. This is 1/3. 1/3, 2/3. Let's see, it'd be a third at a third. It's supposed to look more linear. A little bit bigger third. And let's see, it'd be a third at 2/3, but it's already 1 at 1, so that's taken care of. And now you think about, okay, that takes care of a third. If I have an irrational number that's not any of those, it's going to be less than that. Yeah. No, the value would be the lower. It's 1 over q, and the q there is 3. So it's 1/3 there. So that's where it'd be a third. And then you ask yourself, okay, where would it be a fourth? It'd be a fourth at a fourth. And at 1/2, well, we've already got it figured out there. So it's bigger than a fourth there. In the next place, it would be a fourth, would be 3/4. And you start seeing these lines. You see a little TP-shaped graph there. There's going to be a lot of those things. Now, for example, when I do an 8, I'd have a 1/8 here, but then I'd have these little 1/8s in between, and there'd be the next little TP starting to shape up. But anyway, I'll do the 1/8 one. So let's see, there'd be a bunch of the 1/8s here. So let's see, I got to 1/4. 1/5 would be easy to do. And then if I have an irrational number where that function is 0, I've taken care of all the places where it would be bigger than a fifth. So, of course, my irrational number isn't any of those points. So I can shrink close by and see, oh, yeah, all the rational points in there would be strictly less than a fifth. And I can keep doing this until I make it as small as I want. So it's not terribly hard to see that it would be continuous at irrational numbers. And if you want to read a full-blown paragraph about it, the book writes that out nicely. But the feeling is, there's only finitely many places where it can be bigger than something. And once you realize your irrational number isn't any of them, it has to be less than that nearby at the rational points. Well, today's lesson is on about facts about combinations of continuous functions. And a lot of these theorems are kind of routine. For example, let's call these easy facts. There's two versions of all these theorems. First, you pick a point and say if two functions are continuous at a point, then you can combine them and get a new continuous function. And then the second version would be being continuous on a set, which means it's continuous at every point in the set. And so the previous theorem would automatically imply the next theorem, which is that you can combine functions and get a continuous function on a set by the same token. So I'm not going to write both those theorems. I'm just going to summarize them by saying if F and G are continuous on a set A, then lots of combinations of them are. Then so are linear combinations. C1F plus C2G, where C1 and C2 are constants. f times g. Let's call it 1, 2, f times g would be continuous. And some easy things that just plop out. The absolute value of f and g, absolute value of g, of course, would be continuous. Because if you have those inequalities for f and g, you certainly would have them for the modulus of f, and the absolute value of f and the absolute value of g. Let's see, how about another one? You need to say a little bit more if you're going to divide them by, divide them. So, and if g of x naught is unequal to 0, for when x naught is in A, then f over g would be continuous at x naught. Let's see, all the other ones just follow from rules of limits. The one you have to think about a little bit is number 4. Maybe I'll make a number 5 here since I'm going to just get all these out of the way. Let's suppose if f of x is greater than or equal to 0, then the square root of f of x is continuous. Stuff like that. We've done all these things and we're just taking limits. And so they pop right out when you're talking about continuity. Okay, so let me think about number 4. So they're all easy. The proofs are easy. I should remark in number 4 that you have to know that if g of x is unequal to 0 and it's continuous there, then it's not equal to 0 in a neighborhood. In fact, it's bounded away from 0. For number 4, you need this fact. If f of x naught is unequal to 0, and the limit as x tends to x naught, then you can find a little neighborhood nearby such that g stays away from 0. So there's a delta bigger than 0 such that g of x is bigger than some constant, I should say, and to c bigger than, I'll call it k, and to k bigger than 0. K sounds like an integer. I need and a real number bigger than 0, such that g of x is greater than r when x minus x naught is less than delta and x is in the set we're talking about. Okay, I think I demonstrated that it's the taking a g of x naught over 2 trick. So we've done this, proved this before. The y here, let epsilon equals g of x naught over 2, and just use inequalities and mess around with inequalities. I did it carefully before. Let's see, I think I did it in a positive case. But when you mess around with inequalities, let's see, you can maybe think of two cases. If g of x naught, let's do the strictly positive case. Then g of x naught would look like this. And if I take the epsilon to be g of x naught over 2 and use the definition of continuity, then I would have this tolerance region where the g of x would be stuck in there. And if it's stuck in there, it can't get anywhere near x naught. And in fact, you can see if I take g of x naught over 2, the whole r has to be g of x naught over 2 also. I could take a little tiny epsilon, and then my r would be a little bit bigger. So you can, this is the epsilon distance. This is the g of x naught distance, and I'll make it purple. And of course, if it were negative, I'd do the same picture, but upside down. And you can take the r to be equal to g of x naught over 2, too. If I took epsilon to be g of x naught over a fourth, then I could take r to be 3/4 times that. G of x naught. Questions about that? Let's see. Oh, yeah. Those are kind of straightforward. An even more interesting one is that you can compose continuous functions and get more continuous functions. So let's see. If I have A and B subsets of the real numbers and two functions. Let's take G mapping A into the real numbers and F mapping B into the real numbers. And here's an important thing. If I'm going to compose continuous functions, I need to know that the range of G is contained in the domain of F. So that means, let's see, these things both need to be continuous on the sets. And we need to know that G maps A into the domain of F. The composition is continuous. And F composed with G is continuous on A. Okay, so this that's a critical thing to check when you're going to use this fact. Oh, it's surprisingly straightforward to show this just from the definitions. So let's suppose C is a point in A. Well, then G of C would be in B. And F would be continuous at G of C. continuous at g of c. So given an epsilon bigger than 0, there is a delta bigger than 0 such that let's see, this would be f of y. F is continuous at g of c, so there would be a delta so that f of y minus g of c would be less than epsilon when y minus g of c, what am I saying? Oops, I'm sorry. This would be f of g of c. It's continuous at g of c, so this is going to be f at g of c. When y minus g of c is less than delta. And then you realize, oh, that looks like that also looks like a continuity inequality. But the delta is where the epsilon usually goes. So this thing is going to be a new epsilon. Delta equals epsilon 2. A new epsilon. Okay, and we know that G is continuous at C. So there is a delta bigger than 0. This is a new delta. Let's call it delta 2. There is a delta 2 bigger than 0 such that g of x minus g of c is less than, that new delta is, this new epsilon is epsilon 2, which is equal to the first delta. And now if you put this all together, so this is x minus c is less than this new delta. And so if you go backwards and piece it all together, you get, let's see, so I'm going to let the y be equal to the g of x. And go backwards. And you stick it all together, you realize that you get f of g of x minus f of g of c is less than my original epsilon when x minus c is less than delta over 2. And I guess I should say that x is an A. So it's just a matter of keeping track and using the next epsilon to be a delta. Okay, that's enough of that, I think. I'm kind of eager to skip on to the next section because it's much more exciting and something you haven't thought about before. Questions about messing around with combining continuous functions? Well, let's see, I want to mention it. Consequences before I move on. An obvious consequence is that polynomials are continuous. And if I was going to write a full-blown proof of that, all you'd have to check is that x is continuous. So a book, if I was a book, an easy thing to see, constants are continuous. Duh. Check. X is continuous. Then you can use the epsilon to be the delta. In the definition of continuous. So that's a big fat check. And therefore now I know all these theorems. I can multiply x times x. X squared equals x times x is continuous by the theorem that I can multiply them together and get more continuous functions. So is x cubed, it's x to the fourth, etc. And linear combinations of continuous functions are continuous. So check, that's polynomials. So let's see, so I know that x cubed would be x squared times x. That's another product of previously shown continuous functions, etc., etc. Anyway, it would be tedious. But polynomials are easily seen to be continuous when you combine x with constants. And let's see, rational functions are continuous. But you got to be careful about the denominator. Rational functions, polynomial divided by a polynomial, are continuous where the denominator doesn't vanish. Where at points x where q of x is not 0. That's kind of a no-brainer. Fantastic thing is that sometimes when the q of x vanishes, maybe the p of x vanishes too. And then you can say, maybe we can make it continuous by giving it the proper value at places where it's not defined. And in fact, that's exactly what we do in the difference quotient business. So a difference quotient, if I think about something like x squared minus 4 over x minus 2, that's what you get when you're kind of differentiate x squared. You can factor the top and get x minus 2 times x plus 2. And you see that even in spite of the fact that it looks like a 0 over 0, nearby it's actually approaching 2. So rational functions can be sneaky, where both things might vanish. In fact, I could come up with examples where they even go to 0 or they blow up to infinity if I have an order of 0 in the denominator bigger than the order of 0 in the numerator. Anyway, this is just a remark. That at points where the q of x might vanish, you would have to also think about if the p of x vanishes there. If it does, then you can factor out orders of the zeros and analyze it more carefully. Well, let's see. The book also mentions that sine and cosine are continuous. So the book. Sine and cosine are what's called Lipschitz 1. Lipschitz 1, Lip 1, so that is short for Lipschitz. And consequently, they're continuous. Okay, so what does Lipschitz 1 mean? Let's see, in the case of sine alpha minus sine beta is less than or equal to alpha minus beta. And a homework problem is that if something's Lipschitz 1, then it's continuous. So homework problem. Lip 1 implies continuous. I'll let you think about that in the homework. Let's see, normally when there's a Lipschitz estimate, like that inequality there could be a constant in front. So here's what lip alpha means. It means that f of x minus f of y is less than or equal to a constant times x minus y to the alpha. And alpha should be a positive thing. That's what it means to be lip alpha. Lip 1 is where the alpha is 1. And so normally there could be a c in the definition of lip 1. So in this particular one, the c is equal to 1 in the lip 1 definition. Anyway, Lipschitz functions come up in practice, especially when you start doing Fourier series. Turns out to be a critical concept. And you can prove those inequalities using trig identities for sine and cosine. And it's kind of a fun thing to do. The book kind of bypasses all the fun and just sneaks it out some. So I don't want to dwell on that. I just want you to be aware of that fact. Okay, so now I want to have some more fun with the material in the next section, which is section 5.3, about continuous functions on a closed interval. You learned facts about continuous functions on a closed interval back in freshman calculus. Namely, when you studied max-min problems, you needed to know that a continuous function on a closed interval assumes its maximum. So the big facts, I guess a preliminary big fact, is that a continuous function on a closed interval is bounded. That's kind of something that's very believable. It can't blow up. It can't get gigantic. Okay, that's a biggie. And it assumes it's max and a min. There's a point where those things are attained. And it assumes it's max at points in the interval. this is where the Bolzano-Weierstrass theorem is going to come in a critical way. Okay, that's the biggies. I don't want to try to jam them in the end of the lecture here, but I'll start thinking about them. So maybe I should define some of these things. You can guess that a function f is bounded on a set A means there's a m bigger than or equal to 0, or there is an m such that f of x is less than or equal to m for all x in A. Okay, so now I'm going to show you that fact. Let's say, suppose f is continuous on a closed interval. Got to be closed, otherwise. It's easy to come up with a continuous function that's not. If it had open endpoints, then you could have like a U-shaped thing that blows up at either endpoint. It'd be continuous on the open interval, and so this would be a false thing. Both of those theorems would be false on an open interval, because you could have a U-shaped thing that blows off to plus infinity at the endpoints of an open interval. Or you could have one go down to minus infinity too if you wanted. F is bounded. Okay, well, let's think about it. Suppose it isn't. Okay. Well, then I can't. It's not bounded by 1, for example. So there would exist x1 in that interval where f of x1 is bigger than 1. Well, it's also not bounded by 2. So there is an x2 in AB where it's bigger than 2, etc. You know, x2 might be the same as x1, but eventually if I get up to like 27, let's say f of x1 is 13. When I get up to 27, I get a new point. It couldn't. So eventually, I can't keep using the same points over and over again. So you believe, so etc. I keep doing this. I get a sequence xn of points in AB such that f of xn, absolute value, is bigger than n. Well, x sub n is a sequence in a closed interval. And so the Bolzano-Weierstrass theorem, what's a bounded sequence? So the aha moment here is xn is a bounded sequence since they're all in the interval, so A would be less than or equal to xn is less than or equal to B. And so Bolzano-Weierstrass theorem implies that there's a convergent subsequence. So yields a convergent subsequence. X and K converging to X naught. Well, the interval AB is closed. Meaning it contains all its limit points. I'll say AB contains all its limit points. Cluster points, or accumulation points, whatever you want to call them. What does the book call them? Accumulation points? I like to call them cluster points. Because it's closed. It's closed. That's what it means. And now you think about it, the function is continuous at x naught. So this is the ouch moment. Let's think about it. The f of x and k's would tend to f of x naught. But the f of x and k's are that's contradiction. Because the f and k's are going absolutely bonkers. So think about it. Can't do that because let's think about it. F x and k is going to be bigger than n sub k. And of course the n, so I'm taking a subsequence, n sub k is bigger than k. And so there's no way those are going down to some value. Questions about that? So that's an easier thing to see that it's bounded. Here's a little thing you can do to make the, you can always do something like this. We have a f of nk, absolute value is bigger than k. I could take a further subsequence if I wanted to that either goes to plus infinity or minus infinity. So if you think about that, the set if both those, let's say the set where the set of indices nk where f of xnk is positive, let's call that I plus, or negative, let's call that I minus. Can't both be positive. and can't both be finite. So at least one of them is infinite. And so I could take a further subsequence so at least one of them maybe both of them are infinite, but at least one of them is infinite. That means there's going to be a subsequence that either blows off to plus infinity or blows off to minus infinity. So I can take a further subsequence such that either the f nk is greater than nk, is greater than k rather, so it's obviously going off to infinity. Plus infinity, or xnk, sorry. F of xnk is less than minus k, and that would be the subsequence that goes off to minus infinity. Don't need to do that here because it's clear that there's no way those numbers are converging to anything. But I can make it even uglier, that they blow off to plus infinity or minus infinity, to see that it's even more absurd. Well, you can use a very similar idea. I don't want to jam it in at the end here, to show that these things assume their max. So similar ideas, and I'll do them next time carefully. To get maxes and mins attained. Max or mins. And the key word is attained. Okay, now that we know that the continuous function is bounded, it would have a sup, a supremum, and an infimum value. And I'd have to just show that that value is attained. And that wouldn't, it's not going to be hard at all. And it's going to be another application of the Bolzano-Weierstrass theorem. I'm going to take sequences that get closer and closer to the maximum value, and then take a subsequence that converges and show that the limit of that subsequence is where the thing is actually attained by continuity. So it won't be terribly hard at all. So let's see, in the last key property of sups, so the max, so I will show the max is going to be equal to the supremum. We know this is a bounded set, so let's call this S for supremum. I don't know it's the max yet, but a key property of the supremum I'm going to run out of time. I'm going to start next time with the key property of the sup.